Hi, so today we're going to learn how fiber optics works. And you might have seen fiber optic lines before, and these are essentially strands of optically pure glass. They can be as thin as almost a piece of human hair. It's crazy, and they're really awesome because they can transport information over really long distances. And so they send information, which is essentially coated in a beam of light, down a glass or plastic pipe. And they were actually originally developed for endoscopes. And you might say, okay, well, what's an endoscope? It's just a technology used for helping doctors see into the human body without needing to actually cut open the body. So that was a pretty cool technology in the first place. But it essentially is how we can transmit phone calls at the speed of light to begin with. So in fiber optics, you have what is known as the optic cable, and that consists of tons of different little optic fibers inside. So you can draw those. We can draw those in. So it's several of those optic fibers, and these are thin strands of essentially glass or plastic. And you can have, anywhere from 2 to a couple hundred in one cable. But you might say, okay, well, how does this actual optic fiber or optic cable even work to begin with? And it works because of a property called total internal reflection. And I'm going to abbreviate it here, TIR. So you might say, okay, well, how does this work? This is a method by which reflection occurs, but there are two prerequisites, and I'm just going to refresh ourselves as to what those are. So first, we got to be moving from a more dense to a less dense material. And another way to put that is you have to be moving from a high index of refraction to a low index of refraction. And the reason that is because we need to, we're going to want to make our ray of light bend away from the normal. And if you draw it out, you'll see that this won't actually happen unless you're moving from a more dense to a less dense material. So that's why we have that prerequisite to begin with. Secondly, what has to happen is that the angle of incidence needs to be greater than the critical angle. And so you might need a refresher on the critical angle. The critical angle is just the angle of incidence at which the angle of refraction is equal to 90 degrees. So this is essentially saying that whenever the angle of incidence becomes just a little bit greater than the critical angle, well, then we're going to get some form of reflection because the angle of refraction would then be greater than 90 degrees. So this is what we need for total internal reflection to happen. So let's say here we have our little optic fiber, and inside of it there's this outer layer and an inner layer. So this outer layer is actually known as the cladding. You can see it right there and also right here. And the inside layer is just known as the core. And so what happens is that we have a ray of light that's coming through. Oh, and sorry, what is extremely significant is that on the inside we have a high N, and on the outside we're going to have a low index of refraction. So a more dense core and then a less dense cladding. So when we have a beam of light that comes through, it's going to hit the cladding, and what's going to happen is that it'll actually reflect off of the cladding because there's going to be total internal reflection. So let's check our prerequisites. First, are we going, when it hits this part right here, is it going from a more dense material to a less dense material? Well, yes, we're going from a higher N to a lower N. And the second prerequisite is that the angle of incidence is got to be greater than the critical angle. So if that is the case, what's going to happen is instead of the ray of light just continuing this way, it wouldn't actually continue that way, it would refract, but it's going to bend away from the normal. So here I've drawn a normal right there, and it's going to bend away from it. So as a result, we're going to get this phenomenon called total internal reflection, and that's essentially keeping the beam of light inside the pipe, which is really important. So let's do it again. We have the same situation here. There's our normal, and we're going again from a higher density to a lower density. And because the angle of incidence is going to be greater than the critical angle in this case, the same exact thing is going to happen. The light is going to, instead of going this way, it's going to bend away from the normal. And this is going to be another example of total internal reflection. So it's going to keep doing this and essentially keep traveling through the pipe. So the total internal reflection in this case is really significant because it keeps all of the light inside the pipe. So essentially, when this happens, there's multiple different ways that the light can travel. So I'll draw it in blue over here. If you have a cable and the light only goes essentially straight through in one direction, there's only what is known as one mode, M-O-D-E. And a mode is just essentially a path of traveling. And this is actually what happens, in cable, in your TV, and in your internet. But in another example, we have what is called a multi-mode fiber. So multi-mode. And in this case, there's several different ways that it can travel. It can travel via total internal reflection, like I just described. It can literally go straight through, or it can go at maybe more of an angle. So this is drawn poorly, but that way. So this is used to link computer networks, for example. So there's several different ways that the beams of light can actually travel and hit the ends of the pipe. So there are also some really cool medical applications of this. In a gastroscope, for example, a gastroscope is a type of endoscope, and it is what doctors actually use to detect illnesses in the stomach. So it's essentially a thick fiber optic cable with several different fibers that a doctor will stick down your throat. It has an eyepiece and a lamp at the top. So here in red, we have the eyepiece and a lamp. And let's say this is your stomach and this is your esophagus. Well, they'll stick it down your esophagus and into your stomach. And what will happen is the lens at the bottom is going to be used to reflect the light against your stomach, and it's going to come back from the lamp back into the eyepiece. So that's one application of fiber optics in the medical world today. It's also used to transmit pictures of your organs and your arteries, so it's essentially a camera that can be used. But all in all, fiber optics is this really cool technology that allows us to transmit information at the speed of light, also used in medical applications that we've outlined, and it works primarily through total internal reflection.